Welcome to module 4 of chapter 1. In this module, we define greatest common divisor of two integers and then we discuss an important algorithm called Euclidean algorithm, which evaluates GCD of two integers, two given integers, and then we will discuss an important result called Bézout's identity, which expresses GCD of two given integers as their integer linear combination. In module 4 of this chapter 1, we will introduce greatest common divisor of two integers, Euclidean algorithm and its applications, Bézout's identity and its applications. First, we will define GCD of two integers. Before that, let us define, let n belongs to Z, then we define a set Dn is equal to D belongs to Z such that D divides n. That is, Dn is set of all divisors of n. For example, if you take D8, D8 set of all divisors of 8 are minus 1, 1, 2, 4, 8 and minus 2, minus 4 and 8, minus 8. So, now with this, by defining that Dn, now we are going to define GCD of two integers. First, note that we will take two integers a and b, at least one of them is non-zero. Let a comma b belongs to z minus 0. The greatest common divisor of a comma b is denoted by GCD of a comma b and is defined as maximum of dA intersection dB. That is, GCD of a b is the largest integer d such that d divides a and d divides b. For example, if I take both a is equal to b is equal to 0, then what is going to happen? In that case, what is dA? We know that from the properties of divisibility of integers, every number divides 0. So, dA is entire z, dB is also entire z. Consequently, GCD of 0 comma 0, that is, we defined it as intersection of dA intersection dB and its maximum value of that set, but that is not defined in this case. So, GCD of 0 comma 0 does not exist. So, we should be careful while dealing with the GCD. So, at least one of the integers a and b should be not equal to 0. Since every integer is divisible by 1, so GCD of a b is always greater than or equal to 1. Since we are looking the maximum of among the divisors, so obviously GCD is a positive integer. So, obviously GCD of a comma b is greater than or equal to 1. So, let a not equal to 0, then we have to compute what is GCD of a comma 0. So, in the definition of GCD, one of the integer can be 0, but both cannot be 0. So, now what happens if one of the integer is 0, then in that case what is the GCD of a comma 0. So, it is easy to see that GCD of a comma 0 in this case is modulus of a. We should be little careful, we should not write a, it is because GCD is a positive integer. Similarly, the GCD of a comma a is equal to again modulus of a. Let C belongs to Z, then it is easy to see that the set of all divisors of C is also equal to set of all divisors of minus C. Hence, we have the following result, that is lemma GCD of a comma b is equal to GCD of a comma minus b is equal to GCD of minus a minus b, that is also equal to GCD of minus a comma b, and it is equal to GCD of modulus of a comma modulus of b. That means, all these values are equal. This is the beauty of the way which we defined. We defined GCD of a comma b as maximum of the intersection of dA comma dB. So, we will end up with this lemma. This is easy to show. So, we are skipping the proof of this result. So, since GCD of all these are equal, we may assume that both a and b are positive. Also, since GCD of a comma b is equal to GCD of b comma a, we may assume that a is greater than or equal to b. Also, by ignoring the trivial case, that is GCD of a comma a is equal to a, since we are again please note that here we are assuming a is positive, that is why GCD of a comma a is equal to a. We suppose a is greater than b. So, we have a is greater than b is greater than 0. So, now our problem finding GCD of two numbers boils down to just finding two integers a b, a is greater than b is greater than 0. So, if you are able to find GCD of a comma b with this condition a greater than b greater than 0, then we can find GCD for any two integers. So, this is an Euclidean algorithm. In this algorithm, what we have is, if let a is greater than b is greater than 0, and also if we have a is equal to b q plus r, then we have this condition that GCD of a comma b is equal to GCD of b comma r. So, it is what theorem states is, instead of evaluating GCD of a b, it is sufficient to evaluate GCD of b comma r. That means, we are reducing the size of the integers without reducing their GCD. Proof follows like this. In fact, in this proof we will prove more, that is we will prove that dA intersection dB is equal to dB intersection dr. That means, we will prove that common divisors of A and B is same as common divisors of B and R, then automatically their maximum values are also going to be equal. So, that is why actually the result what we had to show is their GCD of A B equal to GCD of B comma R, but we are proving more, that is their common divisors are equal. So, proof goes like this. To show that, first we will take D divides A and D divides B, that means D belongs to dA intersection dB. So, as we know that in order to prove two sets are equal, we generally will prove that one is subset of other and other is subset of the first one. So, that is we had to show that dA intersection dB is subset of dB intersection dr, and similarly we had to show that dB intersection dr is subset of dA intersection dB. For that we choose it first D belongs to dA intersection dB. So, once D divides A and D divides B, and since another thing which given to us is that A is equal to B q plus R. So, R is equal to A minus B q. So, we know that once D divides A and D divides B, then D divides the integer linear combination of A and B. So, D divides R as well. So, we have D divides R as well as D divides B. So, D belongs to dB intersection dr. So, we proved this one side, that is dA intersection dB is subset of dB intersection dr. Similarly, other way, that is also just follows from the concept that if D divides two numbers, then it divides their linear combination. That is again, we will assume that D divides B and D divides R using linearity of division again, and the fact that A is equal to B q plus R, the linear combination of B and R, we have D divides A, D also divides A. So, D divides A and D divides B. So, we showed that dA intersection dB equal to dB intersection dr. Hence, GCD of A comma B is equal to GCD of B comma R. Euclid's algorithm uses this repeatedly to simplify calculations of greatest common divisors by reducing size of given integers without changing their GCD. Let GCD of A comma B is equal to D, then by division algorithm what we have is A is equal to Q1B plus R1, where 0 is less than or equal to R1 is less than B. Now, if R1 is equal to 0, what happens? If R1 is equal to 0, B divides A, then GCD of A comma B is equal to D, and that is equal to B, and we stop. But if R1 is not equal to 0, then by division algorithm, now division algorithm we will apply for B and R1. So, B is equal to R1 Q2 plus R2, where 0 is less than or equal to R2 is less than R1. If R2 is equal to 0, then again we have D equal to R1, we will stop. That means, GCD of B comma R1 is R1, and then by previous result GCD of A comma B is also becomes R1. So, we got the required result. If R2 is equal to 0, R2 is not equal to 0, then again we will continue in this way. We will get a sequence of numbers like B is greater than R1 is greater than R2 and so on greater than or equal to 0. We must eventually get a remainder Rn is equal to 0 after at most finite number of steps, means at most B steps. It is because B is a positive integer. So, each time even if we will go one step, only one step also, at most in B steps we will eventually reach 0. So, this algorithm terminates. So, since D equal to GCD of A comma B, which is also equal to GCD of B comma R1, which is equal to R1 comma R2 and so on, R1 Rn minus 2 comma Rn minus 1, and from the last equation we have that Rn minus 2 is equal to Rn minus 1 Qn plus Rn. So, which is equal to r n minus 1 into q n. Thus, GCD of r n minus 2 comma r n minus 1 is equal to r n minus 1, that is also GCD for a comma b. So, we will illustrate this with an example. For example, we want to find a GCD of 34 comma 55 55. So, solution will go like this. First, we will use the division algorithm, that is 55 can be expressed as 35 into 1 plus 21. Here the remainder is 21, which is not equal to 0. Then, so we will apply division algorithm for 34 and 21. So, 34 is equal to 21 into 1 plus 13. Again here remainder is not equal to 0. So, we will now apply Euclidean algorithm or division algorithm for 21 and 13, that is 21 is equal to 31 into 1 plus 8, still remainder is not equal to 0, again we have to apply division algorithm. So, we will get 13 is equal to 8 into 1 plus 5, again we will apply for 8 and 5, then 8 is equal to 5 into 1 plus 3, then 5 is equal to 3 into 1 plus 2, and 3 is equal to 2 into 1 plus 1. At last we got 2 is equal to 1 into 2 plus 0. So, that is what we are claiming, that after finite number of steps we eventually get a remainder as 0. So, in this for this problem GCD of, so consequently GCD of 55 comma 34 is equal to 34 comma 21, which is equal to GCD of 21 comma 13 and so on, that is last tuple, that is GCD of 2 comma 1, that is equal to 1. So, the GCD of 55 comma 34 is equal to 1. So, this example again we will illustrate with an geometrically by a figure like this. So, let us take a rectangle with the sides 55 and 34. Then what we are doing here is that the length 55 is divided into 34 and 21. Again now the height is the 34 is divided into 13 and 21, again 21 is divided into 13 and 8 and so on, like that we will going to reduce this rectangle. So, from this geometrical also we can understand that this algorithm eventually terminates and we will get the GCD of 2 integers. As we saw, Euclidean algorithm calculates the GCD of 2 integers by reducing their sizes without reducing their GCD. Euclid gave this algorithm 2000 years back. Still, this is considered one of the best algorithm to calculate GCD of 2 integers. One of the interesting property of this Euclidean algorithm is that it does not use the prime factorization. If you ask a student to calculate GCD of 2 integers, usually he or she evaluates first prime factorization of the both the numbers, then try to evaluate the GCD, but this is not feasible for the large numbers, as still for a given number finding prime factorization for that number is very hard problem. So, but we are lucky that Euclidean algorithm will not use the prime factorization and also gives the GCD of 2 integers. So, that is why Euclidean algorithm attains its authority even now. With this, we will now go to the next result, that is one of the important results called Bézout's identity, and we will see its applications as well. Now, we are ready to prove another important result called Bézout's identity. This result states that if a comma b are 2 integers both not 0, then GCD of AB exists. Moreover, we can find the integers u and v such that GCD of a comma b is equal to AU plus BV. So, as again since GCD of 0 comma 0 does not exist, so that is why we are assuming that one of the integers either a or b is not equal to 0. That means both simultaneously not 0. So, in order to prove this result, we will take a set S is equal to Ax plus By, where x and y are integers. So, if you look at the set, here a and b are fixed integers, x and y are variables. So, x and y are changing. So, it is an infinite set. So, still what we can say more about this set? Since at least one of A and B is non-zero, that we are assuming. So, S is an infinite set. Further, if you suppose that A not equal to 0 and x equal to A and y equal to 0, then we have A square belongs to S. Since one of them is non-zero, so without loss of generality, we are assuming A is not equal to 0. In that case, we have A square belongs to S. Since A is an integer and A square is positive, so we S contains positive integers. So, then from now we can construct a subset of S containing only positive integers. As we know, we will do this to in order to utilize well ordering principle, in order to apply well ordering principle. So, consequently, S contains positive integers as well. So, we will define S dash is equal to S intersection n, then S dash contains only positive integers, which is a subset of S. So, by well ordering principle, S dash has a least element, say D, such that since D belongs to S dash and S dash is subset of S and S is defined as A x plus B y. So, D should be of the form A u plus B v. It is because D is one of the element in S. So, by giving particular values to x and y, you will get the value of D. So, D is now a member of S, in fact in particular it is a member of S dash. So, D is equal to A u plus B v for some u comma v belongs to Z. Now, we claim that D is GCD of A comma B. So, by the least element which we got, the least positive integer in S, that is the GCD we are claiming. This is a nice result and a nice observation that that even though the set S A x plus B y contains infinite number of integers, the smallest positive integer in that is going to give the GCD of A comma B. So, how to prove that one? So, for that, in fact, we will show more, that is we want to show that S is in fact all multiples of D, that is S is equal to D into M belongs to Z, that is it is dZ in fact. So, that means we are proving more than required. Not only that one element D that belongs to S is integer linear combination of A and B, but we are claiming that every element in the set S, in fact it is a multiple of D. So, for that we will choose one element Z belongs to S. Then by definition of S, there exists M comma n belongs to Z such that Z is equal to A m plus B n. By division algorithm, there exists Q comma R belongs to Z such that Z is equal to D q plus R, where 0 is less than or equal to R is less than D. That is what we are insisting, that whenever you come across two integers A and B is not equal to 0, better to apply division algorithm. For example, in this case we have that D is a positive integer. So, D is not equal to 0, Z is any integer. So, because of that we can express Z is equal to D q plus R. Actually, what we have to show, D is a multiple of Z is a multiple of D, that means that we have to show R equal to 0. So, now our objective in the rest of the proof is to show R equal to 0. So, for that, since R is equal to Z minus dq, so Z is equal to A m plus B n. So, and D is also we know that that is A u plus B v. So, R is equal to now A into m minus u q plus B into n minus v q. So, here if you want take a little pause and try to calculate that part. So, R is now what happens, R is again expressed as integer linear combination of A and B. So, that is it is of the form A x plus B y. So, this R belongs to S, and further if you look at the properties of R is less than D. So, this is true only when R equal to 0. Why it is so? If for example, if R is not 0, then R is a positive integer belongs to S, but we know that D is the smallest positive integer in S. So, R has to be 0. So, that means that Z is equal to dq or D divided Z. So, we proved that every element in S is a multiple of D, is other way to say that S is equal to dZ. But we are not proved that D is GCD, just we proved that D is entire set is dz. So, now we will prove that D in fact D is the GCD. For that, let us take C belongs to N and C divides A and C divides B, that means C is a common divisor of A and B. Then automatically C divides AU plus BV again by integer linear combinations property. So, C divides AU plus BV, that is equal to D. So, C divides D. So, other part is trivial, since D divides every element in the set S. So, D automatically divides A, D also divides B. It is because why D divides A and D divides B? It is because A can be expressed as A into 1 plus B into 0. So, A is an element of S. Similarly, B can be expressed as B is equal to 0 into A plus 1 into B. So, B is also an element of S. We proved that every element in S is divisible by D. So, automatically A and B also divisible by D. So, D is also a common divisor, and but we proved that every other common divisor is dividing D. So, D is the greatest common divisor of A and B. So, that is proof is completed. So, now here one of the remark is this: let A comma belongs to Z. Suppose A and B are not both 0, that means at least one of them is not 0, then the argument used in the proof of the above theorem implies that the smallest positive value of Ax plus By is GCD of A comma B. This is one of the important property of Bézout's identity. Now, we will use Bézout's identity to prove different problems. First, we will prove this result, that is GCD of A B comma C equal to 1, then GCD of A comma B C is equal to GCD of A comma B into GCD of A comma C. So, the proof goes like this: we will assume that GCD of A comma B C equal to D and GCD of A B equal to D 1 and GCD of A comma C equal to D 2. So, we need to show that D is equal to D 1 into D 2. So, in order to show this, what we will prove is D divides D 1 into D 2 and D 1 D 2 divides D. So, this follows easily. It is because since D 1 is GCD of A comma B. So, A can be expressed as some n into D 1 for some n, and A is also expressed as m into D 2 for some m, and D 1, since D 1 is a GCD of A comma B. So, D 1 is equal to A x 1 plus B x 2, and similarly D 2 is equal to A x 2 plus C x 2. So, D 1 D 2 is equal to we will get a linear combination of A and B that forces D divides D 1 D 2. Similarly, other part is also similar, since GCD of, now we will use that GCD of B comma C equal to 1, hence GCD of D 1 D 2 is also equal to 1. So, from the Bézout's identity there exists x comma y belongs to Z such that 1 is equal to D 1 x plus D 2 y, or if you multiply both sides with A is equal to A D 1 x plus A D 2 y, and again I will plug in the values of A from above. So, we will get D 1 D 2 into m x plus n y. So, this follows that D 1 D 2 divides D. So, we will prove both the directions. So, D is equal to D 1 D 2. Now, another result is if A comma B are integers not both 0 and k not equal to 0, then GCD of K A K B is equal to modulus of k times GCD of A B. One should be careful again, GCD is always a positive integer. So, we should not take just k, we have to take modulus of k. So, proof again it is straightforward. Here it is just follows from the fact that GCD of A B is equal to GCD of A comma minus B, which is equal to GCD of minus A B, GCD of minus A minus B. So, it is sufficient to assume that k is greater than 0. So, it is sufficient to prove the result for GCD of K A K B is equal to k times GCD of A B whenever k is greater than 0. So, let us take GCD of A B is equal to D and GCD of K A K B is equal to E. So, again we need to show that E is equal to D. So, that follows very easily. Please go through the remaining part of the proof, it is very straightforward. Now, with this we will go to the next result, that is there are many other results like this. We invite you to try to solve all these problems. These are our corollaries to the Bézout's identity. So, now we will go to prove the next result, that is GCD of A comma B equal to 1 and A divides C, B divides C, then AB divides C. Okay. This is very important result. If you look at carefully, what is A divides C, B divides C, then AB divides C. In general, this is not true. Here the condition GCD of AB equal to 1 is required. So, we will see how we utilize it. So, since GCD of A comma B equal to 1, there exists x comma y belongs to Z such that 1 is equal to Ax plus By. This is because we are applying Bézout's identity. So, if you multiply both sides with C, then C is equal to Cax plus Cby. So, actually what we have to show? Again, whenever you are proving the result, just again go to the statement what we have to show. Here we have to show AB divides C, but here we have C is equal to Cax plus Cby. So, we have to show that AB divides C, that means we have to write C is equal to AB into some integer. For that we have to utilize the hypothesis. We are still not yet utilized A divides C and B divides C. So, if you use that one, since A divides C, B divides C, that implies that there exist integers m and n such that C is equal to M A, which is equal to N B. So, if you plug in these values in that equation, C is equal to Cax plus Cby, then what we will get is C equal to AB times some Nx plus My. So, clearly C is equal to AB into some integer. So, AB divides C. Now, we will define a least common multiple of two integers. Let A comma B belongs to Z minus 0, that means both are non-zero integers. Then an integer C is said to be common multiple of A comma B if A divides C as well as B divides C. Let C comma C AB denotes a set of all common multiples of AB, then it is easy to see that 0 belongs to CAB. It is because every number divides 0. So, A divides 0 as well as B divides 0. AB is obviously divisible by both A as well as B, minus AB also divisible by both A as well as B. So, 0 AB minus AB belongs to C of AB. So, by well ordering principle, C of AB intersection N contains a least element. Why we are claiming that C of A comma B intersection N is non-empty? It is because we are assuming A comma B both are non-zero. So, at least one of AB or minus AB is a non-zero and it is positive quantity. So, that is why C of AB intersection N is a non-empty subset of natural number. So, we can apply well ordering principle. So, by that this has a least element, that is what we call the least common multiple of A and B. In short, we will denote it as LCM of A comma B and LCM. It is denoted as square bracket A comma B. As we know that earlier we denoted GCD of A comma as open bracket, and here LCM is denoted as closed bracket A comma B. So, now we will prove an important result which is familiar to you, but we are giving the proof. If A comma B are two integers not both 0, then GCD of AB into LCM of those integers is equal to product of their integers. So, let us assume GCD of A comma B equal to D, then by Bézout's identity there exists M comma N belongs to Z such that D is equal to AM plus BN. Let T is equal to AB by D. So, we have to show that in order to prove that result we need to show that LCM of A comma B is equal to T. So, we will proceed like this. Let A divides C, B divides C, then C is equal to AU as well as C is equal to BV for some U comma B belongs to Z. Now, we will consider C by T. C by T is equal to C times AM plus BN by AB. It is because AM plus BN is equal to D and T is equal to AB by D, from that we will get this result. So, C by T is equal to C into AM plus BN by A into B. So, which is equal to, we are plugging the value of C, then we will get AB VM plus AB UN by AB. So, we VM plus UN, it says that C by T is an integer, that means that T is dividing C. So, clearly T is a common multiple of A and B. So, T becomes a least common multiple of A and B. So, hence the proof. Now, we will end this, in order to end this module, we will define another important definition and one result, small result. The definition is this: let A comma B C belongs to Z, then the equation of the form A x plus B y is equal to C is called linear Diophantine equation, in short LDE. That means all the coefficients are integers and it is a linear equation, A x plus B y is equal to C. We will say that LDE, that a linear Diophantine equation, is solvable if it has a integer solution. We are looking for integer solution. As we know that if you look for real solutions, it has infinite number of solutions. So, we are looking for integer solutions, and further we know that A x plus B y is equal to C. If you draw geometrically, it is a straight line. So, we are looking all integer points on that line. So, for example, 2x plus 4y is equal to 3 is not solvable. It is easy to check. That means there exists no integers x and y such that 2x plus 4y is equal to 3. So, that is why we have this theorem that linear Diophantine equation A x plus B y is equal to has solution if and only if D divides C. It is clear from the definition as well. The GCD of 2 comma 4 is 2, that does not divide 3. So, so it is easy to see that part. So, where D is a GCD of A comma B, if x naught and y naught be any particular solution of this equation, then we can find all the solutions by taking x equal to x naught plus b by d into t and y is equal to y naught minus a by d into t, where t is an arbitrary integer. In this module, we defined GCD and LCM of two integers, and we discussed an important algorithm called Euclidean algorithm and also an important result called Bézout's identity. In the proof of the Bézout's identity, what we proved is the GCD of two integers is their integer linear combination, but in fact we proved more. If you look at the proof of the Bézout's identity, what we proved is the integer linear combination of two integers in fact a multiple of D. That means, if A and B are two integers, then A x plus B y is a multiple of their GCD of A and B. So, with this we will end this module and also the chapter 1.